Hello and welcome to this first lesson of Chapter 5, which is on the geometric applications of differentiation. Okay, so what we're going to be looking at in this chapter, or this lesson of this chapter, we're going to discuss what increasing and decreasing curves are. We're going to practice applying the gradient function just to really ensure you really nail how we're actually using this function. And finally, we're going to talk about defining and sketching our local and absolute critical points and what the difference between those are. Okay, the first thing that we're going to have a look at is increasing and decreasing curves. So I'm going to draw up a curve here, and we're going to talk about what each of the points are. Right, up till this point, you should be able to recognize that at these 2 points here, right, we're going to have a turning point. Right, we call that a turning point because the gradient m is going to be equal to 0 at both of those points. Right, so remember, gradient is always positive, negative, 0, or in some cases undefined. Right, so in these cases, it's going to be 0, and then on each of these sides, it's going to be positive, and in between, it's going to be negative. Okay, so how do you tell if something is going to be a positive gradient or a negative gradient? I always like to think of it like reading a book. So if we look here, I read left to right, as we do. So reading left to right, we go from this point, read right, and the new value that corresponds to that is now higher. If we look here, if we go reading from left to right, here, left, and the corresponding value is now lower, right? So we can see if we look from left to right, that's what gives us the indication of whether it's increasing or decreasing. And just for reference as well, if a curve has a positive gradient, that means it's increasing. If it has a negative gradient, it means it's decreasing. So that's also relative to the direction that you're reading it as well. So always, if it's got a negative gradient, it's decreasing, positive gradient, it's increasing. Okay, so now that we've talked about increasing and decreasing curves, let's just talk about using the gradient function just to make sure we've really nailed it. So find the gradient to the tangent to the curve y equals tan x at the point x equals pi on 8 and give your answers correct to 3 significant figures. Okay, we have the curve y equals tan x, and the derivative of that is going to be sec squared x. If you don't know how to do that, go and have a look at the last chapter where we do differentiation of trigonometric functions. Okay, so now that we've got the derivative, I'm going to rewrite that as 1 over cos squared x, right? Just because this is easier to put into the calculator since they've asked us to do it to 3 significant figures, right? All I need to do now is substitute this value there into that and put it into the calculator. So 1 over cos squared pi on 8, right? If you want to put that into the calculator, it should be 1 over cos pi on 8. And then I believe if you've just put the closed bracket and then the squared, that squares the entire function, not just that, right? So that should give you the correct answer, and that should be 1.17, right? 1.17 should be the answer correct to 3 significant figures. Alrighty, now it's also important to note not just what this answer is, but what this is actually saying. So they're saying find the gradient of the curve y equals tan x at this point. So what that's actually saying is, remember, the tan function has an asymptote at pi on 2. If we go to pi on 8, which is approximately here, it's saying that that line, that tangent to that line, would have a gradient of m is equal to 1.17. Radio. Just as well, if you're doing this question, ensure that you've put your calculator into radians mode, otherwise you'll get a different answer. Okay, moving on. Let's have a look at local critical points. Okay, I'm going to draw up a little diagram here just to show what local critical points means. Okay, so like we spoke about in the last section, this here has a gradient of 0, right? So m is equal to 0. Also here, m is equal to 0, right? We call this point here a local minimum. A local minimum, and this point here, a local maximum. Okay, why aren't these points, why are these points specifically called local minimums? Well, the reason we call it a local minimum is because it's definitely a turning point, so local minimum turning point. So it goes down to a minimum point and then goes upwards from there. But the thing is, it's not the lowest value on this function, because if we have a look down here, if we extended this down further, this would be a way lower function value. And likewise for this point here, it is the highest point locally, but here we would get a far higher function value. So that's why we call them local minimums, turning points, because there's sections on the graph that will be higher or lower respectively, right? We're actually going to have a go at sketching a function just to see how it looks. Right, so the function we're going to sketch is going to be y is equal to x to the 3 minus 3x squared. Okay, so we're going to have a go using differentiation to actually sketch this function here. We'll do some more of this later, but I felt it's good to get right into it. So how do we actually figure out where these turning points are so that we can actually figure out where we're going to draw our graph, so how the graph is going to be shaped? Well, if we know these turning points are at the gradient m equals 0, or when the gradient is equal to 0, what we can do is we derive the function. So y dash is equal to 3x squared minus 6x, right? And now if we let this equal 0, we will get the x coordinates that corresponds to where this function is equal to 0, or where the gradient is equal to 0. And note as well, this function that we're talking about here does not correspond to this one up here. They're different functions. Okay, so this one that we're talking about here, if we let the gradient equals 0, we factorize to solve, so we get 3x outside of x minus 2. So taking out a factor of 3x will leave us with x minus 2 in the brackets. And then to solve this, we can have x is equal to 0, because if we sub 0 into there, we will get 0 as an answer. And if we have x equals 2, if we put 2 into there, we're going to get also the answer, the function equals 0. So we'll get a true statement for both of these cases. Right? Now, to find what points these actually correspond to on the function, right? So now that we've found the turning points of them, now we want to actually look at what points they correspond to on the function so we can have a go at plotting them. All we have to do is sub in the x values back to the function, the original function up there. So subbing in them to the function, f of 0 is going to give us 0, and f of 2 is going to give us 2 to the 3 minus 3 times 2 squared, which is going to be 8 minus 12, which will give us the answer minus 4. Okay, so if we have a look at our function, how it looks right now, we've got a point that goes through 0, 0, and we've got a point that goes through 2 and minus 4. Right, 2 minus 4. Now, we know it's a cubic function. So in this case, we know that cubic functions must have their arrows going in the opposite direction. And we'll talk a little bit about more about that in absolute critical points. But the only way that we could possibly link these together with a positive coefficient of x, which means it's going this way, is going to be a graph that looks like this. Oh, actually, my mistake. That doesn't go through the turning point. Right? With a graph that looks like that. That's the only way that we can link them. Now, don't get too caught up about if you didn't get that straight away. This is just to give an example of how we can use local maximum and minimum turning points. We'll actually look at the proper way to know which direction all of these are facing later on. Right? So don't get too caught up about that. That's what we're going to have a look at later. Okay, and the final thing that we have to talk about is our absolute critical points, right? So what is an absolute critical point? Well, it's where there's a point in the curve which is the absolute lowest you will ever find. Note that on this curve here, so we've got our local maximum and our local minimum there, but even if we keep on continuing this curve, it will continue to get lower, so we'll never get an actual point that is the lowest. It just keeps going on forever, right? So we will never get a absolute lowest point. In a function like y is equal to x squared, we will absolutely get our lowest point. That should go through the origin, right? Because this here at the origin is going to be the lowest point. There's nothing that can actually get lower than that. Every other function value is above that. So if we were to talk about this one here, this would be an absolute minimum. An absolute minimum, right? And in terms of how to actually determine whether something can have an absolute minimum turning point, one thing that we can remember is that when you've got a function, let's say y equals x to the 3 plus x squared plus x, right? Okay, whenever you have a function, this is using some extension 2 knowledge, what will dictate the shape of the function is the highest power of x. It doesn't matter anything else. What will dictate the shape of the function will be that. Now, if this power up here is an odd power, the arrows will go in the opposite direction to each other. So what I mean by that is it doesn't matter how I draw this, right? No matter how I draw this, the arrows in the direction of the arrows I know are going to be correct. They probably won't be the turning points like this, but I know that the arrows will be pointed in opposite directions to that. You can have a go testing some of these on Desmos. It works every time. As long as there is an odd power there, the arrows will be pointing opposite directions. So one will be going down and one will be going up. Right? Also, if there's a positive value of x, the one going up will be pointing this way. If we have a negative value of x, so if we have a negative value, if I put a negative out in front, they're going to go like this way. Right? So this is something that can just help you determine quickly with a bit of judgment if a curve you've sketched looks roughly right. The reason we will only get a absolute minimum if it's an even power is if you have a look at these odd curves, they go in both directions for an infinite amount of time. Like they keep going, they will never stop. Whereas with even powers, what's going to happen is you're going to get both arrows going in the same direction. So something like y equals x to the 4, right? Y equals x to the 4 looks like this. And anything that has an even power is both arrows are going to point up, which means there must be one point on this function that will have a lowest point, right? So the only time you're ever going to get an absolute minimum is when you have an even power. Odd powers will point in the opposite direction to each other. And likewise, if you've got a negative out the front, this is going to point in the other direction. Okie dokie. So what we've had a look at today, we've had a look at discussing what increasing and decreasing curves are, practicing applying the gradient function just to make sure we've nailed that, and defining and sketching the local and absolute critical points.